All right, we're going to do section 2.4 of our calculus book, which is velocity and other rates of change. So in this section, we're going to see instantaneous rates of change, better define that term. We're going to learn all about motion along a line. We'll see sensitivity to change, and finally, derivatives in economics. But we start with 2.4.1, instantaneous rates of change. And there's one new vocabulary word, and it's exactly what the title of this section is, an instantaneous rate of change. So we want to make sure that this phrase is well defined before we go any further in the study of rates of change. So we're going to take a look in this section at some applications where derivatives as functions are used to represent rates at which things change in the world around us. Calculus is often known colloquially as the study of change. So it makes sense here that we see some applications where the derivative that we have just defined is going to help us see change a little bit better. Generally, we think of change as change with respect to time, but it doesn't necessarily always have to be time. For example, a physician may want to know how a change in dosage affects a body's response to a drug, or an economist might want to see how the cost of producing steel changes with the number of tons produced. So there are many different ways where we can compare an independent and a dependent variable and still get a rate of change. So let's begin now with that more well-defined definition of rate of change. So if we interpret the difference quotient, and that's what this is, the difference quotient, as the average rate of change of a function f over the interval from x to x plus h, we can interpret the limit as h approaches 0 to be the rate at which f is changed at the point. And so what we're thinking here again is an XY coordinate grid, and we have our function f. And if we take a look at the interval from x to x plus h, and we take a look at that slope, which is the rise over the run, or in other words, it is f of x plus h minus f of x all over x plus h minus x, which leaves us with h. If we think of this limit where h goes to 0, which means x plus h moves towards x, and this point moves towards the original point, this limit as h approaches 0, this can be then the average rate of change. Well, that leads us now to an instantaneous rate of change. The instantaneous rate of change of f with respect to x at some point a is the derivative, f prime of a. And we know this is the limit definition of derivative. It's conventional for us to use the word instantaneous even when x doesn't represent time. The word, however, is frequently omitted in practice. When we say from here on out rate of change, we're going to mean instantaneous. Just as when we talk about velocity, if we don't say instantaneous before that, we still mean it. When we say rate of change, we mean instantaneous, we mean the derivative. So here's an example. Enlarging circles. We want to find the rate of change of the area A of a circle with respect to its radius. Then evaluate the rate of change at r equals 5 and r equals 10. And finally, if r is measured in inches and a is measured in square inches, what units are appropriate for dA, dr? So let's begin part A, and we're going to need an equation that relates the area and the radius as we move forward. So I think we all know the area of a circle. A is equal to pi r squared. Now, this doesn't ask us for just that. It asks us to find the rate of change of area. So that means we want the derivative. We want to differentiate with respect to, well, in this case, it's going to be r ddr. And here we're going to find the derivative with respect to r, and that's going to give us dA dr, the derivative of a, that's an r, dr, the derivative of a with respect to radius. And on the other side, since pi is just a constant, the derivative of pi r squared is going to be 2 pi r. The 2 from the exponent comes out front as a multiplier, multiplies with the coefficient pi. R is the variable here. Its exponent is reduced by 1. So we have our answer to part A. Part B, we want to evaluate the rate of change of A at r equals 5 and at r equals 10. So in part B, we would like to calculate dA dr at the moment when the radius is 5. So that's going to be a 2 times pi times 5, or 10 pi. And then we want to do it when r is 10. So dA dr at the moment when r is 10 will be 2 times pi times 10, or 20 pi. So notice here that the rate of change in area is larger, 20 pi, when the radius is larger, 10, than when the radius is 5 and the change in area is 10 pi. So I got a Desmos graph. I want us to see that actually in motion. So here's a circle with radius 1 now. I've got the area of that circle calculated below. And notice that as we move the area bigger, the radius is going to start to change at a greater rate. So that time we just went up about 9. Let's move the radius to 3. And there's about 14. Now about what, 22? This time about 28. And now we're over 100, and we've gone up about 40 this time. And you can see as we move that radius larger, now we're up by 50 with just one move. This time we're up by about 60 in area with just one motion. So as the radius gets larger, the area rate of change gets even larger as well. And that's where we're going to stop with our first video in this set.